As we showed in the last section, when the Hermitian operators representing two physical observables commute, they share eigenfunctions. But what happens when the operators do not commute? To understand this, we're going to go back and look again at the uncertainty principle, but this time using the power of the linear algebra we have introduced. We're going to be able to draw a very general conclusion here, though it will involve a rather mathematical proof. This proof is straightforward, but it itself does not offer much physical insight. However, the ultimate result here has profound and broad physical consequences.
First, we need to set up the concepts of the mean and variance of an expectation value. We're going to use more of a statistical notation here. A bar will denote the mean value of a quantity A. So imagine, statistically speaking, we perform multiple measurements on A and we get an average value A bar. Now these are going to be our quantum mechanical measurements when we prepare the system in the same state again and again and try to measure the quantity A, and we'll get an average value A bar. And in bracket notation, for a measurable quantity associated with the Hermitian operator A, then when the system is in the state F that we keep preparing it in to repeat our experiment here, A bar will be the same thing as what we've been calling the expectation value of A, and for a state F, that's just this entity here. F as a bra vector, A as an operator, and F as a ket vector. So let's define a new operator that we're going to call delta A. So this is a mathematical operator. It's related to the operator we had for A. And we're going to have this operator associated with the difference between the measured value of A in any particular experiment and its average value. So that is, this new operator, we're going to define delta A as just the operator A minus the average value. And to be strictly correct here, we ought to have an identity operator in here because this is an operator. But in a somewhat loose notation we tend to use in this kind of algebra, we don't bother to put that identity operator in. So we should strictly write it this way, but in this algebra we mostly won't bother to write that, taking it as obvious it should be there if we've got an expression that's basically an operator. So we take this identity operator mostly to be understood in our algebra. Now, note that this new mathematical operator we've created is also Hermitian. A was a Hermitian operator. A bar, which is just a number times the identity operator, is obviously also Hermitian. So this entire new operator here is also Hermitian. Now, in statistics, variance is the mean square deviation from the average. So to examine the variance of this quantity A that we're going to keep on measuring statistically, we keep repeating our experiment, setting up in the same state, measuring some value for A. We get different answers in general each time we do that, possibly, and we're looking at the variance of the answers that we get. So we're going to be examining the expectation value of a new operator, delta A squared. And let's just check what this does for us. So we're going to expand our usual arbitrary function f on the basis of the eigenfunctions psi I of A, the operator representing the physical quantity. So as usual, we perform our expansion here. And we're going to formally evaluate the expectation value of this operator when the system is in this state F to check out what it does for us. So we have the expectation value of this operator, delta A all squared, by definition, if we're in the state F, is just this form here. And we can expand F in both cases here. Here's our expansion of F that we wrote down. Here's the expansion of the bra vector version of F. Of course, we use a different index in here. And here's our delta A squared operator written out. Well, we can operate with the first one of these, the one on the right in this square here. Operating on this function just gives us Aj, the eigenvalue, minus A, the number here, times psi j. That's straightforward. And then we can do this again. We can operate with A minus A bar on this vector here. We can break it down into parts. So A minus A bar operating on psi j just gives us, again, AJ minus A bar times psi j. So this AJ minus A bar here becomes squared now. And of course, because the psi I and the psi j are members of this orthonormal set here, we only have terms surviving in this sum over I and j when I is equal to j. By the orthonormality of these, that gives us 1 in each case when I and j are the same and 0 otherwise. And so we've just shown that the expectation value of this operator, delta A all squared, is the sum over all the members of the set here with these ci squareds, the modulus squareds of them, the expansion coefficients, times the eigenvalue minus the average answer, just a number, all squared here. So this will be the average value of this squared quantity in our statistics. Now, because, as we said, these modulus squareds of Ci are just the probability that the system is to be found on measurement to be in this state psi I, then this quantity here for that state simply represents the squared deviation of the value of the quantity A that we're measuring this time from its average value. And these are the probabilities that we get these various answers when we do this experiment here. Then, by definition, this quantity here is just this quantity on the right. In other words, we have indeed found that the expectation value of this operator, delta A squared, is indeed the mean squared deviations that we were looking for, the average mean squared deviation that we get. So every time we do our experiment, we prepare it in the state F, we repeat it, we take the answers we get for A here, the measured value, and this operator's expectation value or average here is indeed the expectation value of that mean square deviation from the average. In statistical language, of course, this quantity is called the variance. And the square root of the variance is known as the standard deviation, and it is written like this, obviously. We can call it delta A if we want to. It's just a number here. The square root of the average value of delta A squared. And in statistics, of course, the standard deviation gives a very well-defined measure of the width of some statistical distribution. So it's a good measure of width in the answers that we are getting. We can also consider some other quantity B, some other physical quantity associated with the Hermitian operator B. And similarly, we can write the average value of B that we would see. That's just the same thing as the expectation value. We use this form here if we're in the state F. And with similar definitions, we could define a delta B all squared, and we'd get the same answer for what that meant. So it would also be giving us the variance of the distribution. So we have ways now of calculating the uncertainty in the measurements of the quantities A and B when we do repeated experiments, when our starting system is in the state F. And we can use these results in a general proof of the uncertainty principle. Suppose then we've got two Hermitian operators, A and B, that do not commute with one another. And therefore, from our commutator, we have a commutation rest, some operator C. So in our above definition, the commutator of A and B is equal to I times C. So now we get into a purely mathematical proof here. And to start that, we're going to choose some arbitrary real number. This can be any real number that we like. We'll call it alpha. And we're going to define this quantity. This is just a number, g of alpha. So alpha is just a coefficient in here. And this is what we're going to define this quantity g of alpha to be. So we've got alpha times delta A here, the operator, minus I times delta B operating on F. And we're putting that whole thing in bra form. And similarly over here, we have it in ket form. Now, we've written it in this form here, in the ket, to emphasize that we mean this vector. All we're saying is that the result of alpha times delta A minus I times delta B operating on F is just a vector. And this expression here is just the inner product of that vector with itself. So mathematically, this whole thing here is just a vector. It's an operator operating on a vector, which gives us, therefore, a vector. So this whole thing here is the inner product of a vector with itself. And therefore, this must be greater than or equal to 0. So this is just all mathematics here for the moment. But this is a mathematically correct statement. And we're writing it this way for the moment just to emphasize that this thing here is just a vector and this thing here is just a vector. So, as we said, it has an inner product with itself, and that has to be greater than or equal to 0. So, if we write this out here, as we just have from our previous view graph, we know this has to be greater than or equal to 0. And now we are going to work with this here. The Hermitian adjoint of all of this stuff here is just the sum of these two Hermitian adjoints inside here. So the Hermitian adjoint of I times delta B would be minus I times delta B Hermitian adjoint. And with the minus sign in front here, that ends up flipping those signs round. And by hermiticity of these operators, A and B, of course, that means, and the delta A is also Hermitian, that delta A dagger is just the same thing as delta A, and similarly delta B dagger is just the same thing as delta B. So we make that change here in the algebra. And now we multiply these out. So delta A with an alpha in front of it times delta A with an alpha in front of it is just alpha squared delta A squared. And similarly for the I delta B times minus I delta B, that's just also delta B all squared. And then we have two other terms here. We have I delta B times alpha delta A. So that's this term here. We've got our minus signs here to straighten all that out. And we have alpha delta A times minus I delta B. That's this term here. Well, this here is just the commutator of delta A and delta B. And we know that the commutator of these, by definition, we're going to have that as IC here. So that means that we can rewrite this in the following form down here. Therefore, this whole expression here we can rewrite as the following, because F delta A squared F is just the average value of delta A squared, our variance, and we've got an alpha squared here. And similarly, F delta B squared F is just the average value of delta B squared. And F alpha CF is just alpha times the average value we would see for the quantity C. And that, by definition, is the expectation value of C, F in the bra form, C in the operator form, and F in the ket form, as usual. Now, we're going to do a rearrangement of all of these terms here. It's not going to be an obvious rearrangement, but it will work, and it's quite easy to check that it does work. So we're making this non-obvious rearrangement. All of this set of terms here is exactly the same as this set of terms here. So how does that work? Well, notice here we've written alpha plus C bar over 2 delta A squared bar, and we squared all of that. Well, obviously that gives us an alpha squared, and that alpha squared is this term here because we're multiplying out the front. And it also gives us a term that looks exactly like this, but with a plus sign in front of it. That's a square of this term here. And because we've added that term in, we are cancelling it out by putting minus that same term over here. And then the rest of this square here simply turns into the alpha C bar, and you can check that out. We're going to get 2 times C bar over 2 delta A all squared. And because we've got the delta A all squared, the bar here out the front, that just is the equivalent of this term here. So we have rearranged everything here into this form down here. And of course, as before, this still must be greater than or equal to 0. All of this, as we said, is greater than or equal to 0, must be true for arbitrary alpha. That was one of our assumptions up the front. Alpha could be any real number that we liked, and we could still see this statement is true. So it's true specifically if we happen to choose alpha equals minus c bar over 2 delta a squared bar. And that makes this term here just be 0. So therefore, what we're left with from all of these terms here, we can rearrange them very slightly. We're left with delta a squared bar times delta b squared bar is greater than or equal to c bar squared all over 4. Or equivalently, delta a times delta b is greater than or equal to mod c bar over 2. So, for two operators, a and b, corresponding to measurable quantities a and b, and for which the commutator of a and b is equal to I times some operator c, in some state f, for which c bar, that's the expectation of c, is written out like this, of course, we have the uncertainty principle that delta a times delta b is greater than or equal to the modulus of c bar all over 2. This is our general statement of the uncertainty principle, and here delta A and delta B are the standard deviations of the values of A and B that we would measure. So this uncertainty principle is quite general for any operators A and B where we can evaluate their commutator, and we see therefore that we get an uncertainty principle if the operators do not commute. And we've managed to prove this without presuming Gaussians or any other specific form for distributions. This is generally true. Only if the operators A and B commute, that is, A and B have a commutator that is 0, or strictly speaking 0 times an identity operator, or possibly if they do not commute, they have a commutator rest, but we're in a state f for which this expectation value of the commutator rest is equal to 0. Only in those cases is it possible for both A and B simultaneously to have exact measurable values.
So now we have a very general result. Whether or not the operators associated with two physically measurable quantities commute with one another determines whether or not there's an uncertainty principle between them. This is a core concept in quantum mechanics. Indeed, one can take the view that it's this absence of commutation between such operators that is the real mathematical distinction between the classical and quantum worlds. In the mathematics of classical mechanics, attributes like position, momentum, and energy, and angular momentum are represented by numbers or ordinary vectors. The multiplication of numbers commutes, as does the dot product of vectors. But for the quantum mechanical view, we have introduced operators for these attributes, and the multiplication of these does not in general commute. Whenever that commutation is absent, we have an uncertainty principle for those attributes, a very non-classical idea, at least for those particular attributes. Some people even take the view that it's the postulation of these so-called commutation relations that's the real core set of postulates of quantum mechanics, that this is the real difference between the classical and quantum descriptions.